Sagittarius A is a supermassive black hole at the center of our Milky Way galaxy. Its mass equals about 4 million suns. For years, SGAR A* has been a focal point for astronomers and astrophysicists. Understanding it is crucial to unraveling the mysteries of our galaxy. New research has now suggested something groundbreaking. SGAR A* may have been formed by a massive collision between two black holes billions of years ago. This discovery could rewrite our understanding of galactic evolution. It opens new doors to the hidden dynamics of the cosmos. The idea of such a collision is both mind-blowing and thrilling. It challenges long-held beliefs and presents a fresh perspective on how supermassive black holes come to be. Let's dive deeper into this cosmic revelation and explore its significance. Sagittarius A* sits at the very heart of the Milky Way. It is surrounded by a dense cluster of stars. This region is known as the Galactic Center. The black hole exerts a powerful gravitational force on nearby stars and gas clouds. This force keeps the galaxy in shape. For decades, scientists have studied the behavior of stars around SGAR A*. These observations have helped confirm its existence and mass. However, the origin of SGAR A* has remained a mystery. Traditional theories suggested it formed from the collapse of a massive star. Recent research is painting a different picture. Evidence now points to a dramatic past, involving a colossal collision. Two smaller black holes may have merged to create the supermassive SGAR A*. This theory is based on new data and advanced simulations. Understanding the true origin of SGAR A* can provide insights into the formation of other supermassive black holes. It also helps us grasp the dynamic processes at play in the universe. Imagine two black holes, each with masses millions of times that of the Sun. They are on a collision course, spiraling towards each other. As they get closer, they release immense amounts of energy. This energy is in the form of gravitational waves rippling through space-time. The final moments of the collision are cataclysmic. The black holes merge, creating a new, even larger black hole. This is what researchers now believe happened billions of years ago at the center of the Milky Way. The result was Sagittarius A*, our galaxy's supermassive black hole. This theory is supported by recent gravitational wave detections. Instruments like LIGO and Virgo have observed similar black hole mergers in distant galaxies. These observations provide a precedent for such colossal events. They also offer clues about the environments in which these mergers occur. The idea of SGAR A* being born from a merger is a paradigm shift. It suggests that supermassive black holes can grow through successive mergers of smaller black holes. This process could be more common than previously thought. To understand the formation of SGAR A*, scientists have turned to both observations and simulations. Advanced computer models simulate the dynamics of black hole collisions. These models help predict the outcomes and signatures of such events. Observational data comes from telescopes that observe different wavelengths of light. For instance, radio telescopes can peer through the dust in the Galactic Center. They provide a clear view of the stars and gas clouds orbiting SGAR A*. X-ray telescopes detect emissions from hot gas near the black hole. Combining these observations with simulations gives a comprehensive picture. Researchers can trace the history of the Galactic Center. They can identify signs of past mergers such as unusual star motions or gas distributions. This detective work is like piecing together a cosmic jigsaw puzzle. Each piece of data adds to our understanding of how SGAR A* came to be. It also sheds light on the broader processes shaping our universe. Galactic evolution reimagined. The discovery of a black hole collision at the heart of our galaxy changes our view of galactic evolution. Traditionally, galaxies were thought to grow by accumulating gas and forming stars. New research suggests galaxies grow through mergers, not just of stars and gas, but of black holes as well. These collisions can significantly impact the structure and evolution of galaxies. When black holes merge, they release energy that can influence their surroundings. These effects shape the galaxy's appearance and evolution over billions of years. These events have shaped the Milky Way into the galaxy we see today. The ripple effect on astrophysics. The discovery of SGAR A's collision origin has far-reaching implications for astrophysics. It challenges existing theories and models of black hole formation and growth. It also opens new avenues for research. One of the key implications is the role of gravitational waves. These ripples in space-time carry information about black hole mergers. They provide a new way to study these events and their aftermath. Future gravitational wave detectors will be crucial in this research. Another implication is the need to revise our models of galaxy formation. If black hole mergers are common, they must be incorporated into these models. This requires new simulations and theoretical frameworks. The discovery also highlights the importance of multi-messenger astronomy. This approach combines different types of observations, such as gravitational waves and electromagnetic radiation. It provides a more complete picture of cosmic events. Future black hole research. The revelations about Sagittarius A* open new frontiers for black hole research. Future studies will focus on detecting more black hole mergers. This will help confirm the frequency and impact of these events. Advanced gravitational wave detectors will play a key role. Projects like the Laser Interferometer Space Antenna, or LISA, will detect mergers in distant galaxies. This will provide a wealth of data on black hole populations and their evolution. Observations in different wavelengths will also be crucial. X-ray and radio telescopes can study the environments around black holes. They can identify signs of past mergers and their effects on surrounding gas and stars. These efforts will require international collaboration and advanced technology. The next decade promises to be an exciting time for black hole research. We are on the brink of discovering new aspects of these enigmatic objects. Technological advances and their role. The study of black holes has always been driven by technological advancements. The recent discoveries about Sagittarius A* are no exception. They rely on cutting-edge instruments and techniques. Gravitational wave detectors like LIGO and Virgo are prime examples. They have revolutionized our ability to observe black hole mergers. These detectors can sense tiny distortions in space-time caused by these events. Advances in computer simulations are also crucial. High-performance computing allows researchers to model complex black hole dynamics. These simulations provide insights that are impossible to obtain through observations alone. Telescopes that observe different wavelengths of light are equally important. They provide complementary data that helps build a complete picture. Future advancements in these technologies will continue to drive discoveries. Theoretical implications and models. The discovery of Sagittarius A's collision origin has profound theoretical implications. It challenges current models of black hole formation and growth. It also requires new theoretical frameworks to explain these processes. One key area of research is the conditions that lead to black hole mergers. What triggers these events? How common are they? Answering these questions requires new models and simulations. Another area is the impact of black hole mergers on their surroundings. How do these events influence star formation and galaxy evolution? Researchers will need to revise existing models to incorporate these effects. These theoretical advances will be crucial for interpreting future observations. They will help us understand the broader implications of black hole mergers. They will also guide the search for new black hole populations. The human element in cosmic exploration. Behind every discovery in astrophysics is a team of dedicated scientists. The revelations about Sagittarius A* are no different. They result from years of hard work, collaboration, and innovation. These scientists come from diverse backgrounds and disciplines. They include astronomers, physicists, engineers, and computer scientists. Their combined expertise enables breakthroughs in our understanding of the cosmos. The human element is also evident in the international collaborations. Projects like LIGO and Virgo involve researchers from around the world. This global effort is essential for tackling the biggest questions in astrophysics. The story of Sagittarius A* is a testament to human curiosity and ingenuity. It shows how we can unravel the mysteries of the universe through teamwork and perseverance. Conclusion: a call to curiosity and discovery. The discovery of Sagittarius A's collision origin is a milestone in astrophysics. It challenges existing theories and opens new avenues for research. It also highlights the dynamic processes that shape our galaxy. This discovery is a reminder of the vastness and complexity of the universe. It sparks curiosity and encourages further exploration. There are still many mysteries to unravel and many questions to answer. Future research will build on these findings. It will use advanced technology and international collaboration to push the boundaries of our knowledge. The next decade promises to be an exciting time for black hole research. Let this discovery inspire us to keep exploring and questioning. The universe is full of wonders waiting to be discovered. Let our curiosity guide us on this journey of cosmic exploration.